which is force over area. So let's first off look at this very straightforward picture that we've looked at several times already in this topic, and that's of a pipe narrowing. On the left, there's a wide pipe at position 1, and on the right, there's a narrow pipe at position 2, and water's flowing from left to right. And we've already learned using the continuity equation that as the pipe narrows, as the cross-sectional area decreases, the speed increases. Well, what would increase the speed of the water? We know that it happens, but there has to be some mechanism by which it's happening. If something speeds up, if something changes its velocity, we know there must be some net force acting on it. Well, what's applying forces in a fluid? Water pressure is applying forces. So there must be something about the pressure at spot 1, which is on the left, and pressure at spot 2, which is on the right. So we're going to switch back over to our favorite simulation. This is that fluid pressure and flow simulation from PhET. And specifically, we're going to look at the flow tab, which we looked at already. But this time, we're going to really focus on that pressure gauge up there on the top. And as we widen and narrow the tube and increase or decrease the speed, we want to look at see what happens to the pressure. We're also going to change the vertical position of the pipe and see if that changes the pressure, which if you think back, it would make sense that the vertical position would change the pipe because we know that vertical position or depth in a fluid changes the pressure. So let's head on over to that simulation. Here we are at the fluid pressure and flow PhET simulation. We've clicked on the flow tab, and what I have is a tube filled with water, and it's horizontal, and the water's moving from left to right. And I'm going to take a pressure gauge and measure the pressure at various spots in the tube. I'm going to first notice that if I have the pressure gauge high in the tube, that the pressure is lower than if I have the pressure gauge deep in the tube or low in the tube. And that's just what we learned earlier this unit, that pressure is proportional to depth in a fluid. But what we're really focused on in this, with this simulation this time, is what happens to the pressure as I change the speed of the fluid, and what happens to the pressure as I change the vertical position of the pipe. So the first thing we want to look at is what happens to the pressure as we change the speed. Well, how can we change the speed? We know that we can change the speed of a fluid moving in a pipe by changing the cross-sectional area. That's what continuity equation tells us. So if I want to decrease the speed, I'm going to put the pressure gauge in the middle, left and right of the tube, and the middle vertically of the tube. And I'm going to widen that section of the tube. Notice that the pressure is 121.026 kilopascals. I'm going to widen the tube. And as I widen the tube, the speed of the fluid decreases, and you'll notice the pressure increases. I could also decrease the cross-sectional area, which I'm doing on the left side of the pipe now. If I decrease the cross-sectional area, the speed is going to increase. I know that because of the continuity equation. But if I scooch my tire pressure gauge from the middle where it's wide to the left side where it's narrow, you'll notice that the pressure has dramatically decreased. The speed increases, the pressure decreases. When I move the pressure gauge back to the middle, which is wide, the speed is low and the pressure is high. So those two quantities, pressure and speed of the fluid, are inversely related to one another. As I increase the speed, I decrease the pressure. As I decrease the speed, I increase the pressure. Let's reset this. And I've reset it such that it's now horizontal again. And what I want to do is I'm going to increase the left side of the pipe, increase the height of the left side of the pipe, and I'm going to decrease the height of the right side of the pipe. And I want to measure the pressure at the high end, which is the left end, and I'll measure the pressure in the middle of the tube to be 110.786 kilopascals. And when I move it to the lower spot, you'll notice that the pressure is increased to 127.114 kilopascals. So that makes sense because I'm deeper in the water in effect, but the lower the vertical position, the greater the pressure. The higher the vertical position of the pipe, the lower the pressure. So if I put all those quantities together, which we're going to in just 1 second back on the slide deck, we'll get Bernoulli's principle. Let's head on back over there. So here we go. This is Bernoulli's equation, and it's a very long equation. We're going to really be focused in maybe physics one and talking about what happens if we increase or decrease values. So if I look at the left side of the equation, notice that I've got the pressure at some particular spot, spot one, let's say. I've got the density, that's rho, times the gravitational field strength, times the vertical position at spot one, y1, plus 1/2 rho v1 squared, that's the velocity at spot one. You'll notice as I look at these, this really looks like mgy, which is gravitational potential energy, and this really looks like 1/2 mv squared, which is kinetic energy. And so if I think about what's going on here, really what I'm doing is I'm taking and dividing by a volume. And what's kind of fascinating is if I divide mgy by a volume, I'm going to get rho gy. And so we're talking about like a volume of stuff moving around. So we've got pressure, gravitational potential energy sort of quantity, kinetic energy sort of quantity is equal to those same quantities on the right side of the equation. Pressure 2 at position 2, rho gy2, that's the gravitational potential energy in effect at spot 2, and then 1/2 rho v2 squared, that's the moving kinetic energy at spot 2. So if we were to do a quick practice and look at that question again, what happens to the pressure and the speed as the pipe narrows? Well, I know according to the continuity equation that the speed is going to increase with a decrease in cross-sectional area. I also know, according to Bernoulli's equation, that as the speed increases, the pressure decreases. And you'll notice here that I really don't have a change in vertical position. And so since I don't have a change in vertical position, the rho gy element of the left and right side of the equation is going to be equal, even though I've got some water down here moving up and some water down here, up here, I should say, moving down. On a whole, this water is still at the same vertical position.